Okay. Um, Welcome to the review class for probability. So let's start with what we set up to do in this class, which was to define a probability space or probability triple, which is given by omega, f, and p. So omega, we refer to the sample space. And this sample space has to contain all the possible outcomes of an experiment. Okay, so if we are trying to model a particular experiment, the sample space omega, which is just a set, has to contain all the possible outcomes of an experiment. And so this is the example of having the numbers 1 through 6 on a dice, or having heads and tails in a coin. Okay, now the slightly weird thing is f, which is the measurable event, and is a sigma algebra of subsets of omega. And P is a probability or probability measure. Okay, so P is going from F to 0, 1. Okay, so what are the axioms that we have seen? So as we said, F is a sigma algebra of subsets of omega. So this means that F is a subset of the power set of omega. Okay, so this is called the power set of omega, which are all the subsets of omega. Contains all the possible subsets of omega. Okay, and F is a sigma algebra, which means A1. This is axiom 1. The full set omega is in F. A2, A complement if A is in F, then A complement is in F. And A3, if A1, A2, so this is a countable sequence of events in F, then the countable union from I equals to 1 up to infinity of AI is also F. Okay, so these are the three axioms, and we'll talk a bit about what we can do with these axioms. So what we have said is that by the Moivre rules, this is the Morgan. By the Morgan, we have that the union of A and B complement is equal to A complement intersection B complement. So in particular, by using these guys, and so using A2 and A3, what we can see is that intersections and complements are all contained. So what we can say is a property is that intersections, countable intersections, are also in F. Okay. All right. So then, what about P? So P, the axiom for P is that P is a probability measure if P of omega, let's write it, if P of omega is equal to 1, and for every countable sequence of disjoint events, the probability of the union I equals to 1 up to infinity of AI is equal to the sum from I equals to 1 up to infinity of the probability of AI. Okay, so one thing I should comment, but it's probably clear to you. So the axiom is saying countable sequences, and here I'm taking to illustrate an infinite one. But this also holds for union of 2 events, 3 events, and any finite n. So here, when we are taking a disjoint sequence of events, we can take a disjoint sequence of 2 events, 3 events, and they don't actually need to be an infinity of them. Okay. Okay, so so this is what it called. This thing is called the additivity property, sigma additivity property for disjoint events. So the sigma sort of notation always denotes that it has to be countable sequences, that the property is valid for countable sequences of disjoint things. So this is sigma algebra. If you want an algebra, instead of having countable sequences, you would have finite sequences, and finite unions are also in F. That's an algebra. Sigma algebra is adding the part of countable into the definition. Okay, so sigma additivity property for disjoint events, but actually for any events A, comma B, the probability of A union B is going to be equal. So this is by using the axioms of by using the sigma additivity property. This is going to be the probability of A plus the probability of B minus the probability of A intersection B. So in particular, because this guy, the probability of A intersection, has to be positive by the properties of the probability, this is bigger or equal than the probability of A plus, this is less or equal than the probability of A plus the probability of B. So in particular, this is to say that in general, P is subadditive. Okay, so what does this mean? Whenever we have the union of the probability of A and B, then this is actually less or equal than the probability of A plus the probability of B. Okay, and it's only equal if A and B, if the intersection of A and B has measure 0. Okay, so if and only if this is equal to 0. Okay, what are other properties that we've seen in class? We know that P is upper and lower continuous. This is something I called Borel-Cantelli, which is not quite Borel-Cantelli, but it's the flavor of Borel-Cantelli, which is that if we have a sequence A1 contained in A2, contained in A3, all the way up to infinity, then the limit of I equals the limit of I going to infinity of the probability of AI is going to be equal to the probability of I equals to 1 of AI. Okay, so we have an increasing sequence, A1, A2, A3, so this is A1, A2, A3, and we keep going. So at the end, if we consider the union of all of them, we will have the limiting set. Okay, so each AI is approximating the limited set from below. Okay, so this is upper and lower continuous. The upper and lower continuous I don't think are quite standard ways of saying it, but anyways, the point is of saying that when the AI are growing, if we take the union of all of them, this is a set A, the probability of the union of all of them is going to be the limit of the probability of each one of them. Okay, but you need to have this property that they're all contained in each other to be able to do this. Okay, and the other, this is going from below, and going from above, let's call it, is P is continuous from above and below. I think that's more standard way of saying it. Okay, so this is from below because this is all of these sets AI are contained in the limiting set. So then you are going, this is always the probability of AI is always less than the probability of A. Okay, so these guys are increasing. And from below, we would have that B1 contains B2, contains B3, and so on. So then the limit of the probability of BI, I going to infinity, is going to be equal to the probability of the intersection of all of them. I equals to 1 up to infinity of BI. Okay, and so this is from below, and this is from above. Okay, so you have a similar picture, but here this would be B1, this would be B2, and then you keep going in until this A1, which is the intersection of all of the BI. Okay, so these are probably one of the most important properties of the probability because you can write a lot of the problems in terms of infinite intersections or infinite unions of growing and decreasing sets. What else do we have? So another thing that we looked at was conditional probability. Okay, so this is whenever the probability of an event V is positive, we can consider the probability of A given B. Okay, so how does the fact that we know that the event V has occurred affect the probability that A will occur? Okay, and this is going to be the probability of A intersection B over the probability of B. Okay, so this is knowing that B has occurred. What is the probability that A will have occurred? Okay, and morally, this is a way to measure this. Okay, so from conditional probability, we did a couple of theorems. So the theorem of composite probability. I don't particularly like that word, but okay, anyways. Which tells you that the probability of a finite intersection, A1, A2, all the way up to AN, is going to be equal to the probability of A1 times the probability of A2 given A1 times the probability of, and this is dot dot dot, the probability of AN given A1 intersection A2 and intersection. So this is a way of like thinking. So the fact that all of them have happened, you have to have that A1 has happened, and then A2 has happened given that A1 has happened, A3 has happened given that A1 and A2 has happened, and so on. Okay, so this is the way of understanding this in a more in a language way, and this is usually used in a bunch of the exercises to try to get what is the probability of these guys by decomposing it into these conditional probabilities, which can be much easier to understand. Okay, so what is the probability of like having two heads? Okay, so that's a little bit of a trivial thing, but of having two heads given that you already had some other thing occurring, and so then you can decompose this intersection in a bunch of little pieces which are easier to analyze. Okay, that's the idea. Okay, what other thing falls from the axioms that you should definitely know is the law of total probability. Which tells you that if, so let's consider BI, which is a countable sequence, I equals to 1 to infinity, satisfies that is the union of I equals to 1 up to infinity of BI is equal to omega, and intersection BI intersection Bj is equal to the empty set for every I different from J, then the probability of A is going to be equal. Okay, so this sequence of set events Bi has to be contained in your sigma algebra F, sigma algebra of events, and the probability of A is going to be the sum of I equals to 1 up to infinity of the probability of Bi times the probability of A given Bi. Okay, so just to give you a graphical representation of this, so if this is your sample space omega, and now we divide omega in a bunch of small pieces, B1, B2, B3, and so on, and now we have a set A, we can write A as a bunch of disjoint union between the different pieces. Okay, so now you can write A as a disjoint union of A intersection BI, I equals to 1 up to infinity. So then the probability of I is the sum of these disjoint, the probabilities of these sets. And the other thing that we should know by conditional probability is that the probability of the intersection I intersection B is the probability of B times the probability of A given B. Okay, the probability of A intersection BI is equal to the probability of BI times the probability of A given BI. Okay, so that's how you show this thing here. Okay, so independence of events, it's quite an important concept. So independence of event is that the fact that B has occurred doesn't affect the probability of A occurring, which implies the fact that B has occurred doesn't affect the probability of A occurring. Okay, so this is A, that is to say, A is independent from B. Okay, so if we want to rewrite this in math, this is that the probability of A given B is the same as the probability of A. Okay, but this guy is just the probability of A intersection B over the probability of B. Okay, so another way of rewriting this is if and only if the probability of the intersection is the product of the probabilities. Okay, so you can either give this definition or this definition. The problem with this definition is that this would not include zero sets with zero probability, and this guy could actually include things with zero probability. Okay, so this is pairwise independence. But we have the notion of independence for a family. So let's say AI with I in I, and I not necessarily countable. Is an independent family if for every finite subset J subset of I, then the probability of the intersection of I in J of AI is the product of I in J of the probability of AI. Okay, so this is independence for the full family, which is different from pairwise independent. Okay, so you could have a family which is pairwise independent, so that means that whenever you take two sets, they are independent, but that doesn't imply that for every finite subset you can actually do this. Okay, so one thing that we proved, so a property. Now I'll write it in a simple case. If A comma B are independent, then A comma B complement are independent. So then A comma B complement are independent, and in general, A complement B and A complement B complement, so let's put it like this, are also, sorry, A complement B complement are also independent. Okay, that's another theorem we proved in class. So the idea is if you have two sets that are independent, the complements are also independent. So, I mean, if you go at the way that the fact that B has occurred doesn't affect the probability of A occurring, so the fact that B has occurred or not has occurred, which is B or B complement, it's kind of telling you that if P of A given B is equal to P of A given B complement, which is equal to just P of A. Okay, so independence is basically telling you the fact that B has occurred or it doesn't occur does not affect the probability of A occurring at all. All right. Okay, so in a bunch of exercises, we have done a lot of counting. So let's call this counting analysis. So a lot of the cases in probability at the end of the day have to do with being able to count how many events have a certain property. So in general, we can think of the case of the case that the probability space is uniform. So we have omega finite and the probability of an event, so omega is finite, f is equal to the parts of omega, so this is like the simplest case for the sigma algebra, and the probability of an event A happening, which is any subset of omega, is going to be the size of A over the size of omega. Size of A. So the size of A is number of elements. Okay, so when we have these cases, we're going to say that this is uniformly distributed. So P is uniformly distributed on omega. Okay, so basically the probability of omega 1, so the set omega 1 is equal to the probability of omega 2 for every omega 1 comma omega 2 in omega. Okay, so the probability that each one of the things will happen has equal probability. So when you roll a dice, each one of the events is as likely to occur. So the probability of having a 1 is the same as having a 2, 3, 4, 5, 6, and so on. Okay, so the point is that when you have these things, the questions of probability start becoming to being able to traduce a word problem into being able to count them. Okay, so the things that you will need to be using is, so basically quantities. Okay, so we have 2 to the n subsets of a set of size n. Okay, so this is basically if you have the size of omega, which is equal to n, then the power set, the size of the power set of omega is equal to 2 to the n. Okay, and this is including the empty set. Okay, then you have n to the k. the sequences of k elements of a set of size n. Okay, so n to the k are the sequences of k elements of a set of size n, and this is allowing for repetitions. Okay, sometimes we will allow for repetitions and sometimes we won't. Okay, so then the thing that is related but is slightly more complicated is the nk, which is going to be n factorial over n minus k factorial, which is just n times n minus 1 times n minus k plus 1. Okay, so this is all products. And in this case, these are the sequences of size k of a set of size n, not allowing for repetitions. Okay, so let's say that we throw a dice k times. The amount of possibilities of what things could come up is n to the k. Okay, so n is 6 and k is the amount of times that we throw a dice. If we throw a dice one time, the possible outcomes are 1 through 6. If we throw a dice 2 times, we have 6 squared, which is 36, and so on as k increases. So if we want to find the amount of the probability that there is no number that is repeated, then we have to have n to the k over nk. Okay, so this is the probability that we throw a dice and each of the numbers is different, when you are going to have to take n is equal to 6 and k is the amount of times you had thrown the dice. Okay, of course k has to be less than 6, if not this should be equal to 0. Okay, and then finally n k, the combinatorial number, is just n factorial over n minus k factorial times k factorial, is the subsets of size n of size k of a set of size n. Okay, so basically this thing does not allow for repetition and does not care about order. Okay, so this the point is that the quantity of subsets has to do also, you have to care about the order. When I say sequences, there is an order to them, and n over k doesn't actually take into consideration the order of how they came out. Okay, so this was maybe the first half of the stuff we were doing. So the next thing that we looked at was random variables. Okay, and this is something that already became remote learning. So random variables. So random variables, and we usually denote it by x, is a function that is going from your sample space onto R, such that the inverse Okay, so this is the inverse in terms of sets of an open set minus infinity, let's say V is, oh, let's call it with a close, is an event for every V in R. Okay, so this is the definition of being a random variable. So this is the same as saying that X is measurable later on. So the idea is that these random variables are a way of sort of compressing the information. So maybe we do not want to know exactly what omega happened, but we care about an observable. Okay, so this can be seen perhaps as an observable, which is to say we don't care about which specific element of omega we got, but we care about a quantity associated with the specific element that omega we got. Okay, so the example that we had given in class is if you pick a person in a city or in the world, maybe you don't care about the specific person, but you care about like doing some statistical analysis of what's going on with their height, so or their weight. So X can be the height of the person, and Y could be the weight of a person. Okay, so the only thing that we care, I mean, this restriction here is trivial. So the restriction is trivial if F is equal to the parts of omega. Okay, so in the case that we have in the discrete space where the sigma algebra is the whole parts of omega, then this restriction is trivial. Okay, it doesn't actually matter. Now, what do we look about this? We looked at the distribution function. So f of x is f of x, which is going from R to R, is the distribution function of x if sorry, and this is going from R to 0, 1, if the f of b is equal to the probability of x less or equal than b for every b in R. Okay, and one of the, okay, so it's clear that this has to be between 0 and 1 because the probability is always going to be a number between 0 and 1. Okay, so what are the properties of f? So the properties, or let's call it, so what we've seen is that f is a distribution function. So f from R to 0, 1 is a distribution function of a random variable if and only if f1, f of a is less or equal than f of b for every a less or equal than b. So f is non-decreasing. So f2 is that f is right continuous. So if we have a that is here and we have a sequence coming from the right, so this is a1, a2, a3, so basically an is converging down onto a, then limit when n goes to infinity of f of a n is equal to f of a, and f3 is that when you go the limit when a goes to plus infinity of f of a has to be equal to 1. On the right it has to be equal going to 1, and on the left limit when a is going to minus infinity of f of a is equal to 0. Okay, so you have a distribution function of a random variable if and only if you satisfy all of these properties. Okay, so what do we look at next? So for this exam what we looked at discrete random variables. Okay, so this is what we center of, because these are a bit easier than continuous random variables, is that there exists S, which is countable. There exists X S countable, such that the probability that X is in S is equal to 1. Okay, so here we have to be a bit careful, because omega is not necessarily discrete. Omega is not necessarily discrete, so then even if you have a continuous probability space, it could be that your random variable is discrete. If you look at the possible outcomes of X are always within a countable set. But this is different from saying that the image is exactly just a countable set. So if we look at A such that the probability of X is equal to A, the probability of X equals to A is positive. This has to be contained in S, and this gives you, this is like, and I should put quotation, this is like the image of X. Okay, it's not quite the image of X. X could have, the image of X could be slightly larger, but the ones that count are only the ones that have a positive probability. So you could rearrange X in such a way that its image is only given by this. Okay, so these are discrete probability functions, and so associated with them, they have a function, a probability function associated to discrete random variables. There exists, let's call it little f x, which is going from R to 0, 1, such that, I say random variables, we have fx going from R to 1, the mass function, which basically f of x of a is just the probability that x is equal to a, and this is for every a in R. But the idea is that the mass function will only have mass, or will only have a non-trivial number for a, so f of x of a is positive only if a is in the image of x. Okay, so this brings us to the other things that we defined, like the expected value, expectation. So the expected value of a discrete random variable, so the expected value of x is going to be the sum of a in the image of x of a times fx. Okay, so this gives you an idea of what is the expected value of your random variables. So if you take an experiment, then around which value would you expect that x is lying? Okay, so now this gives you some sort of average behavior of x, but we can also look at like this is a property or maybe a lemma that we prove. So the lemma is that we have g that is going from R to R, then the expected value of g of x, so this is a function applied to x, is going to be the same sum within the image of x, but now instead of a, we are going to have this function g of a fx a. Okay, and the example that we usually have used is when g of a is equal to a squared, so then the expectation of x squared is going to be the sum of a in the image x of x squared times fx a. Okay, so yeah, this is just the probability that x is equal to a. So what are the properties we have seen of expectation? So what are the properties? If x is bigger or equal than 0, then the expectation of x is bigger or equal than 0. So these are saying if the image of x is always positive, then you're having this sum a f(x) x of a only over the positive things, and so all of these numbers are positive, so then the expectation has to be positive. What else? The expectation, so this is what I call linearity. So linearity is telling you that the expectation of alpha x plus beta y plus gamma, okay, so alpha, beta, and gamma are numbers in R, is going to be equal to alpha expectation of x plus beta expectation of y plus gamma, okay? And this is, we don't need independence, okay? So observation, we do not need independence. Okay, what else? Something that we do need independence for is if x comma y, this is another property, if x comma y are independent, then the probability, the expectation of x times y is equal to the expectation of x times the expectation of y. Okay, and usually when you have this property, what we have said, looked at last class, was that this means that they are not correlated. Okay, so morally this is saying that if x increases, it does not imply that y increases. Okay, so what we saw last time, it was a way to measure what are the increases of x doing in terms of the increases of y, but something we won't look much in the review now. So what else should I say? Before I go to variance, so one of the points is that we have looked at examples of discrete random variables that you should know. So you should know that the examples of discrete random variables. So basically what we're saying is that a discrete random variable is completely determined by the mass function. Okay, so when we write, so the examples that we have seen is that sort of x sort of distributed like a Bernoulli random variable with p. This is that f of x of a is equal to p if a is equal to 1 minus p if a is equal to 0, and 0 otherwise. Okay, so we say that x is a Bernoulli variable with parameter p if its mass function satisfies this. So in particular, we can calculate the expected value and just by looking at this formula here. Okay, so this is one example. The examples that you should know are Bernoulli, geometric, which is like when will the coin flip ahead for the first time. Okay, so this is geometric and it has one parameter p. Then we have Poisson, that this has to do more with the half-life of decaying probabilities, but anyway, so this is Poisson and we denote Poisson lambda, and so here we have that f(x) of a is going to be lambda to the k factorial times e to the minus lambda. Okay, so sorry, this is fx of k, and k is in 0, 1, 2, and so on. Okay, so this is Poisson. We saw geometric, Poisson, and then we have binomial, and p. And these are all the ones that you should look into and actually study for the test. Okay, what's next? So I should mention, actually I didn't say it here, so this type of properties and most of the properties I've said here, except the ones that I haven't covered in class, you should actually know the proofs for. Okay, as the exam is going to be online, I'm not going to perhaps ask the exact proof I gave in class, but I'll give a slightly variation of the same idea. Okay, so the next thing is that if expectation, so the next topic is variance. If expectation gives you an idea of the outcome for x, then the variance tells you how likely you are from that expectation. Okay, I guess somebody decided to honk their horn today. So how do we define variance? So the variance of x is the expectation of x minus the expectation of x squared. Okay, so basically the variance of x is measuring in a squared sense the differences between the outcomes of x and what we expect x to come out. Okay, and so this, as we saw by the properties of expectation, so this is the definition, and this follows as a property that this is just the difference between e of x squared minus e of x squared outside. So what are the properties of this? So the properties is that one is the variance of ax. This is not actually linear but quadratic, is a squared times the variance of x. And the second part is that if x comma y are independent, then the variance of x plus y is equal to the variance of x plus the variance of y. So one should actually check that. So this follows from the property that the expectation of xy being independent implies expectation of xy is equal to the expectation of x times the expectation of y. But this is only true when x and y are not correlated or they are independent. So if they are not correlated, then you can have that the variance of x plus y is equal to the variance of x plus the variance of y. So in general, it's not true that the variance of x is equal to the variance of x plus y. So in general, variance of x plus y is not equal to the variance of x plus variance of y. So be careful, maybe in some exercise you have to be careful of not making this mistake. Okay, and the couple of things that we've seen is for the particular examples. For the particular examples, we have that if x is so let's put it on the other side. So for the particular examples, what do we have? So if x is Bernoulli with parameter p, then the expectation of x is p, and the variance of x is p times 1 minus p. If x is Poisson with parameter lambda, then expectation of x is equal to lambda, and the variance of x is equal to lambda. Then the other thing that you should know is that if x is being binomial with parameters n and p, then expectation of x is equal to n times p, and the variance of x is equal to 1 p times 1 minus p times n. And if x is geometric with parameter p, then expectation of x is 1 over p, and the variance of x is 1 minus p over p squared. Okay, and then finally, from the things we've seen this last class, So from last class, we looked at like joint distributions. Okay, so we had x and y not independent random variables. So we had the joint mass function, so f of x comma y of a b is the probability that x is equal to a and y is equal to b. Okay, so here the expectation of x times y is going to be the sum over the image of x times of the sum over the image of y of of a times b times fxy of a b. So whenever we take any function of x and y, so in this case is the product, what we are going to get, so we have the expectation. So now we have g that is going from R2 to R, and we take the expectation of g of x comma y. This is the sum of g of a b times f of x comma y a b. Okay, so this will be helpful in general whenever we have random variables that they are not independent, okay? So this has to do with what we were saying before. Sometimes the expectation of x times y is not the expectation of x times the expectation of y. So, the last thing that we should know is the inequalities. So inequalities. Okay, so this quantifies what is the probability of something happening. So Markov inequality is the probability. So x has to be bigger or equal than 0. The probability that x is bigger or equal than a is less or equal than the expectation of x over a. Okay, so this is Markov inequality. And similarly, using Markov inequality for a function, we have the probability that x minus ex absolute value is bigger than a. So, and this is the notion of variance, so how far you are from your expected value is going to be less or equal than the variance of x over a squared, okay? And this is Chebyshev's inequality. Okay, so I think that is all that will be covered in the exam. I'll try not to make it so hard, but this is morally the idea of what's the topics that are going to be there.